Hello, more on equations for lines. So here's a graph of the line y equals 2x plus 3. Wow, thrilling. So I just want you to notice a couple things. What's the y-intercept of this line? The y-intercept is where it hits this vertical y-axis, so it's 3. And what's the slope of this line? Well, let's see. Start at this point. You run 1 and you go up 2, or rather you go up 2 and over 1. So the slope is 2 over 1, which is 1. Okay, so you see what I'm getting at? That's the intercept, and that's the slope. In general, this is always the case. Okay, I spoiled the punchline, but that's always how it is. So now if I just ask you, okay, give me a line with slope m, you remember we use m for slope, and the y-intercept is at 0, b, and I ask you for an equation, that's it. That's the equation, y equals mx plus b. So that's probably the most famous, commonly used form for an equation for a line. It's weird, but we call ax plus by equals c standard form, but you actually don't see that one as much as this one. So it's kind of a bad name. So the slope-intercept form of a line is just kind of the main default form for the equation for a line. So you just kind of have to remember what that is. Like on the test, if I ask you, okay, leave your answer in slope-intercept form, you just have to remember that it's this one. And just remember it's the one with the slope and the intercept. It's the simplest, like I guess most intuitive way to have an equation for a line, because you actually get information from it and just y is on one side. Okay, so there are a couple different ways to do this, but here's, I guess I would say, the best way. Find the slope and y-intercept of the line 4x minus 3y equals 12. Now you could graph it using the intercepts. This would be easy to do. So that's what I mean. That's what's called standard form. But it's faster just to get it in slope-intercept form, because to do that, all you have to do is get y on one side. And you know how to do that. So solve this equation for y. Subtract 4x from both sides, and then just divide the whole thing by -3. Voila. So you get y equals positive 4/3 x minus 4. So then you just remember, okay, that's slope-intercept form. So it may be in your mind, when you see slope-intercept, just think solve for y. Get y by itself. And then you'll just automatically have it. So m, the slope, is 4/3, and the y-intercept is -4. So now let's graph it. So this is a fast way to figure out the slope, figure out the intercept, and then you have everything you need to know to graph the line. So just put the intercept. The intercept is down here. It's kind of small at -4. And then the slope is 4/3. So remember what that means. It's rise over 1. So you're going to go up 1, 2, 3, 4. Sorry, 1, 2, 3, 4, and then over 1, 2, 3. So then just put another point here at 3, 0. It's just a coincidence that happened to be the x-intercept. That's not always going to be the case. But as soon as you have another point, wherever it is, just go ahead and draw the line, and you're done. Okay? So that's a good, quick way to find all the information out about a line, and then to sketch a graph of it. Okay, that's pretty much that. I do want to do a story problem. And this is more of a modeling problem. This is pretty important in math, and we're going to do a lot of it as we get more concepts. So car rental costs $75, like a flat fee, plus 10 cents per mile. I don't know if that's realistic. So this is going to be a multi-parter. Write an equation that represents the cost of renting a car, and we're going to let the cost be y. Okay, so this is linear. Just think about it. It just goes up very regularly. If you drive 1 mile, it costs $75.10. 2 miles, it costs $75.20, right? It just ticks up by multiples of 10 cents. So think about that, what I just said, ticks up. So the line's going to go up pretty slowly. It's just going to go up 0.1 every mile or every unit of time, or distance, I guess. So 0.1 should be the slope. Okay, so we'll put it in terms of x. We could call, well, don't call it m because m means slope and that's confusing. So call it x. So no matter what, you're going to pay $75. In other words, if you drive 0 miles, well, why did you rent the car? You're going to pay 75. So if you think about that, when x is 0, y is 75. So right there, that's the y-intercept. That's like where it starts. Since it costs an additional 10 cents per mile, that's the slope we already established. Okay, so now, knowing what we know about slope-intercept form, the easiest way to pop this into an equation is just to use that. So it's going to be 0.1x, right? It's mx, so 0.1x or 0.10x, but the 0 doesn't do anything, plus the intercept, which is 75. And please ignore these typos here. Don't look at them. Okay, so that's the equation. Y equals 0.1x plus 75. So now we have a very convenient way to know, okay, if I drove, 60 miles or whatever, how much would I end up paying? You just plug 60 in for x and do 0.1 times that plus 75. Ultimately, what I want to do is get a nice graph of this cost. I think let's do a little bit of math first. Right. So we can do what we just said, and we can also kind of do it backwards. If you rented a car and you paid $87.50, how many miles was that? How far did you drive? So remember, x is the miles, y is the cost. So that's going to go in for y. So you're going to do $87.50 equals 0.1x plus 75, and you're going to find the miles, which is x. Like that. You see it? So now it's like with these problems, I'm having you set up the equation yourself. 87.5 is 0.1x plus 75. Solve that for x. That's easy. Subtract 75 from both sides. I like to flip equations around because I like my x on the left-hand side. And then just divide by 0.1. Pro tip, dividing by 0.1 is the same as multiplying by 10. So you don't need a calculator. So x is 125 miles. Okay, and then for part C, I'm going to ask you to give me a nice graph, and this is important. So a couple things to note before we get started. Like, don't just plug this into your calculator and draw what you see. You should know how to graph using your calculator. That's kind of a separate lecture. But it's not going to look right. And even if you get it to where you can see the line on the screen or whatever, that's still not a good graph. So a good graph does a couple of things. It shows all the relevant information. It makes sense with what the problem is, and then it gives you kind of some sense of the scale. So the main thing is, if x is 0, that's not like super realistic, but it's feasible. I guess it's humanly possible. But if x is negative, that's not. Right? So if you show me a bunch of negative values for x on this graph, that's a wrong graph. You're representing things that don't exist, that aren't humanly possible. You can't drive negative miles like you're in Tenet or something. I guess at some point they would start paying you if you drove enough negative miles. Okay, so that doesn't make any sense. So that's the first thing. Your graph should start with x being 0. You shouldn't see any of the stuff to the left of the y-axis, because that would be negative x's. So there shouldn't be any kind of line there. And in fact, we don't even need to see that at all because there's nothing there. It obviously doesn't make sense if y is negative either, but we also know that y is going to be 75 and up, and that will be represented on our graph. So if we made x and y the same scale, like we wouldn't really see the line until we got up to y equals 75, right? And we want to see miles that are less than 75. So we want to scale it. We want to shrink one of the axes. So like miles can be like 1, 2, 3, 4, 5, whatever. But the cost we want to be is going to be bigger than that. Is going to be 75 plus. So we're going to shrink down the y-axis. There you go. And whatever graphing utility you're using can do that. So in fact, if you want practice graphing and messing with your calculator, try and just match this exact graph I've just made. I use a computer, but whatever. So you're going to go into Window and you're going to adjust your X min and X max and Y min and Y max to match the screen. And if you did it right, it's going to look exactly like that. Not as good without the grid. Okay, so you see what I mean? You shrunk down the y-axis. So like these are 10s, whereas on here they're just like 2 or something. Yeah. Okay, so the scale is different. Again, if it weren't, well, then these would go up in 10s, and you know what? For this problem, I guess it would actually still kind of work. But I feel like this is more representative of what it really looks like. Okay, so and there's no line back here, and then we don't even see the second quadrant, right? The first quadrant, remember quadrants? The first quadrant is the only one that makes any sense in this problem, so we don't even want to see the other ones. And a lot of the times that's the case. If you have something happening over time, especially if that something can't be negative, like a lot of real things can't, you're really only dealing with the first quadrant, so nothing else makes any sense to see. All right, and then that's not very much slope, right? It's only going up by 0.1. So our graph represents that. You can see that it is going up, but not a lot, not a lot. Okay, so definitely practice a few of those because I'm definitely going to have you do that on the next exam. Okay, set up an equation and give me a nice, like realistic looking graph of it. Thank you.